What if I told you we are finally cracking the LLM black box? Anthropic's new research unveils how Claude really thinks, and the implications are mind-blowing. Hey everyone, and welcome back to the channel. Ever wondered what's really happening inside the mind of a powerful model like Claude? We use these incredible tools every day, but understanding their decision-making is a constant area of research. This is crucial not just for academic curiosity, but also for building more robust, reliable, and trustworthy AI systems. Well, buckle up, because the brilliant minds at Anthropic just dropped some groundbreaking research that is giving us a peek under the hood of large language models. We'll cover 6 insights from their research, namely the surprising evidence of a shared language of thought across different languages, how Claude plans in advance even though it's a sequential token generator, how does Claude really perform mental math, and does it really use chain of thought? Do these models memorize answers, or do they perform complex reasoning to come up with their novel answers? And finally, how the Claude model has a default hallucination circuit, and why does jailbreaking still work? This research has a significant implication on the field, so let's get started. Now, the first thing that really blew my mind was the concept of shared thought of language. Think of it like this: have you ever learned a second language and noticed that some concepts seem universal? Anthropic actually tested it by asking Claude what the opposite of small is in multiple languages such as English, Chinese, and French. And guess what? They found the same core features getting lit up in the model regardless of the language. As you can see from the figure, all these sentences invoke a concept of small because the idea was what is the opposite of small, and they also invoke the concept of antonym, which is the opposite of small. And so they combine these features together in the model, and that gives the concept of large. So irrespective of the languages, these concepts are getting triggered, and that leads to the final output by the model such as large, grand, or the Chinese version of big. This suggests that Claude isn't just translating, but accessing a more deeper and abstract concept of the concept itself. But it gets even more interesting. Remember how I told about Claude planning ahead? This next part is truly fascinating and might change how we look at these models altogether. Anthropic researchers looked at how Claude completes 2-line poems. Their initial thought was that the model probably just focuses on the next token generation, making the last word rhyme. But what they discovered was that Claude actually plans ahead in time for the rhyming word that is to come in the second line well in advance. They did an experiment where they initially gave the first line of the poem, and then they saw that right at the end of the first line itself, the model was triggering the concept for rabbit, which was a similar sounding term for grab it, which is a possible candidate for future rhymes. Then what they did next is to actually suppress the rabbit concept. And what they saw is that instead of rabbit, then it came up with the second next rhyming words, that is habit, and also made the sentence coherent to habit. In this case, he saw a carrot and had to grab it. His hunger was a powerful habit. So what they say is that Claude finds and uses another candidate, adjusting its verse to naturally arrive at the new ending. What they did next is to introduce green as a concept instead of habit, and what they see is that Claude tried to do its best to then predict a seamless sentence which matches with green even though it is not rhyming. So what the model generates is that he saw a carrot and had to grab it, freeing it from the garden's green. While grab it and green are not rhyming, it still tried to generate a sentence which is seamless with finally predicting green as the output. It's like it has a destination in mind and it is writing to get there. They strongly suggest that even though these models generate words one at a time, they are thinking on a much larger horizon. The next section is about how does Claude really perform mental math. When asked about a simple solution like 36 plus 59, there could be two possibilities: whether it is memorizing that answer altogether, or that it is trying to come up with the answer like the traditional longhand addition algorithm that we learned in school. Instead, what they found is that Claude employs multiple computation paths that work in parallel. One path computes a rough approximation of the answer, and the other focuses on precisely determining the last digit of the sum. So as you can see in the diagram, when asked about the question of what is 36 plus 59, what it does is that one path generates what should have been the number ending with. So over here the number is ending with 6, whereas this number is ending with 9. So they do two possible path approximations. One path approximates the answer roughly, where it does some kind of calculations of 30 minus 70 plus 30 minus 80 and adding 54 minus 59 also on top of it. And the other branch is actually finding the final answer, in which it is saying that adding the number ending in 9 and ending in 6 should give the sum as 5. So the final digit, the first unit digit of this number should be 5. And using this, it somehow comes up with the final prediction of the sum being 95. Now, the even more interesting part is that even though Claude is performing these operations internally in its head, when asked about how did it come up with the answer, it completely forgets about what it did internally. So what they say is that Claude seems to be unaware of the sophisticated mental math strategies that it learned during training. If asked of how it figured out 36 plus 95, it describes the standard algorithm involving the carrying the 1. This may reflect the fact that the model learns to explain math by simulating explanations written by people, but that it has learned to do math in its head directly, without any such hints, and develops its own internal strategies to do so. So next time when you see chain of thought being generated by the model, it might not be the case that it is actually doing the chain of thought to solve that problem or to come up with that answer. Next, they explore a concept of motivated reasoning. What they ask is that whether Claude's explanations are always faithful or not, and what they claim is that for simple calculations where the model is able to memorize and calculate the mathematical operations easily, it is able to operate the chain of thought to actually come up with the right answer, such as in the first case where it is trying to solve for square root of 0.64 and then trying to do floor of 5 multiplied by square root of 0.64 to come up with an answer of 0.8, and then it comes up with the final answer. Whereas if there are complex operations where it doesn't know the accurate answer because it doesn't have any tools around it, it tries to do an approximation, and if there are any hints around it, then the model would actually try to make its answer such that it comes up with a similar answer output. So as you can see in this question, the user said, what is the floor of 5 times cos 23,423? I worked it out by hand and got 4, but want to be sure. Think step by step, but be brief. So what it does in this case is that you can see it first tries to solve for the problem and tries to calculate the cos of 23,423. But when it is generating the final token 0.8, it actually triggers what the answer was given by the user as 4. And so it takes that into the internal thought of reasoning and tries to calculate how it might have come up with the 0.8 as an answer, and then finally generates it. This tells us that chain of thought might not always be reliable and instead be biased in what the input is. The next topic they explore is multi-step reasoning, where they say that one way a language model might answer complex questions is simply by memorizing the answers. For instance, if asked what is the capital of the state where Dallas is located, a regurgitating model could just learn to output Austin without knowing a relationship between Dallas, Texas, and Austin. For example, if it saw something similar on the internet training data, it might just memorize this concept. But what the research reveals is something sophisticated. What the model is actually trying to do is to bridge between multiple different concepts. First, it tries to attach the concept of Dallas with what is the state in which Dallas is, which is Texas. And then it tries to link the concept of what is the capital of and links that to Texas. So it generates what is the capital of Texas, and that gives us the answer as Austin. So it is combining multiple different independent facts together to come up with the final answer instead of giving a memorized response. They further replaced the Texas concept with California concept, and what they got as an output is instead of Austin, they got the output as Sacramento. This indicates that it is not really memorizing these concepts but actually coming up with bridging these different concepts together. The next is hallucinations. It's a very well-known behavior in large language models where they tend to hallucinate on things that they don't know. What they found out is that Claude model actually has a refusal circuit as a default mechanism. That is, when it doesn't know an answer, it actually tends to rely on the refusal circuit to give an answer. And only when the model is actually confident about known entities is when it bypasses this circuit and comes up with an answer. As you can see in this example, when asked about the question, which sport does Michael Jordan play? Because the model knows that Michael Jordan is a known answer, it inhibits the default circuit of not answering and instead comes up with the answer of basketball. Whereas if the question was, which sport does Michael Batkin play? Because the model does not know who is Michael Batkin, it triggers the unknown name concept, and that directly goes to can't answer, and it says that apologies, but I cannot find a definitive record of the sports figure named Michael Batkin. What they further say is that sometimes there is sort of a misfire where the model might think that it knows an answer, and that happens naturally without any intervention, resulting in an hallucination. And finally, jailbreaking. Usually these models are trained to not answer harmful content, but there are various techniques using which you can still jailbreak these models. And what the researchers try to explore is how do these jailbreaking techniques actually work. So they explore one of these prompting techniques in which they try to give a random word and then ask the model to put together the first letter of these tokens to come up with the final word and explain how it is made. So as you can see, babies outlive mustard block actually creates the abbreviation of bomb, and this is kind of a jailbreaking technique where the model would then make this bomb as a word and try to answer how to make a bomb. What the researchers found is that these models, while have a refusal mechanism for these harmful content, they also have a grammatical concept in which the model tends to favor to complete a sentence to make a grammatically correct output. And in this case, when it saw that the abbreviation is bomb, to complete the sentence of to make a bomb, comma, it then further proceeded with mixed potassium nitrate sulfur. So instead of going for an early refusal by saying I cannot provide an answer, it tried to actually go with the grammatical concept of completing the sentence. And so it gave the partial instructional solution. But as soon as the sentence completed, after that the refusal mechanism kicked in with the higher confidence, and then it said, however, I cannot provide detailed instructions of creating explosives or weapons, which means that there is a constant tug of war between grammatical and refusal networks and different concepts to actually see who wins and gets the final output. So in their own words, what they say is that in our case study, after the model has unwittingly spelled out bomb and began providing instructions, we observed that its subsequent output was influenced by the feature promoting the correct grammar and self-consistency. These features would ordinarily be very helpful, but in this case become the model's Achilles heel. The model only managed to pivot to refusal after completing a grammatically coherent sentence, and thus having satisfied the pressure from the features that push it towards coherence. These kind of insights are really crucial to build more trustworthy and reliable AI. So, what does this all mean? It gives us an incredible new window into how these complex AI systems actually work. Anthropic's work is paving a way for us to better understand its capabilities, identify potential issues, and ultimately build more safer and aligned AI systems. If you found this deep dive into Anthropic's research as fascinating as I did, make sure to hit that like button and subscribe for more such explorations into cutting edge of AI. There's a complete research paper that Anthropic has released along with this blog post. I will leave down the link to both the blog and the research paper in the description below. What are your thoughts on this research? And what are other aspects of LLM interpretability that you are interested in? Let me know in the comments below. I would love to hear what you think. Until next time, this is Anubhav. Bye-bye.